Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 38, and it is entitled Vibrating Systems and Simple Harmonic Motion. You'll see sometimes that simple harmonic motion is referred to as SHM, and our classic kind of model for this is going to be a mass on a spring. But it turns out that it will apply to any kind of system that undergoes vibrations. It could be a pendulum, it might be a string, but we're going to model it in the simplest case with masses on springs, and you will see that probably in some form on your AP exam. Let's begin by reminding ourselves of some things that we know about masses on springs. We're going to begin with ideal springs that push masses horizontally on frictionless surfaces. So I have myself a spring here which has some natural length. It's neither compressed nor stretched, and to that spring I'm going to attach a mass. We say that the spring has some stiffness K, the spring constant, usually measured in newtons per meter, how much force it takes to stretch it a certain distance. And the mass we'll measure in kilograms, and these two are going to be important characteristics of our system. Let's suppose that I stretch the spring somewhat and I pull the mass to the right. In this diagram, we're going to call the original position of the left side of the mass x equals 0. In other words, the spring is neither compressed nor stretched at that point. Now I pull it to the right a distance x, so I have stretched the spring by a distance x. When I do that, there is some force that's required to hold the spring in that position, and we say that that force is equal to K times X. That's the Hooke's law force. Technically, there should be a negative sign there showing that the direction of the force is opposite the direction to the displacement, but I'm working in magnitudes right now. I have given the spring now a certain amount of elastic potential energy, which is equal to 1/2 kx squared. And now if I let this spring go, it's going to oscillate back and forth. And the kind of motion that it's going to undergo is called simple harmonic motion. We'll define that more specifically in a moment, but I'm going to have repetitive motion. The mass is going to gain speed as it approaches the equilibrium position, and then as it passes by it, then it's going to lose speed as it compresses the spring on the other side. It's going to convert its elastic potential energy into kinetic energy, and then the kinetic energy back into elastic potential energy. And there's going to be this interchange between energies. If this is a frictionless system, this is a conservative system. There's only the spring force acting to accelerate the mass, and we can say that the total energy of the system is conserved. Just for completeness, I'm going to write down what the kinetic energy formula is because we're going to use it in a few minutes. I'd like to show an animation of this. This comes from a website from the University of California at Irvine. Here we see a mass that's going back and forth in simple harmonic motion, and we can follow the shadow of that mass. It turns out that there are other things that can execute simple harmonic motion, such as a pendulum here. I have a simple pendulum that's oscillating back and forth. Or, if you think about the shadow of this, we can talk about uniform circular motion. Look at the shadow of this ball. In all of these cases, these objects are undergoing what we call simple harmonic motion. And the kind of curve that will be traced out is a repetitive curve. So back to the mass on the spring, you can see that if I follow the shadow, I'm going to be tracing out a sine curve or a cosine curve. And depending on where the object is at the beginning of my stopwatch, then that's going to determine whether I have a sine or a cosine. For a simple pendulum, I have a similar sort of situation, a sine or a cosine curve. And likewise, for uniform circular motion, I get the same sort of tracing out of the shadow of this object showing a sine or a cosine. We say that simple harmonic motion occurs when I have some system, whether it's a mass on a spring or a pendulum or some other system, in which the force that drives the system back towards equilibrium is directly proportional to the displacement. The big deal in this is the fact that we have a directly proportional relationship. In other words, the force is proportional to the displacement raised to the first power. And that's what we have in Hooke's law. The force, F, is equal to K, some number that multiplies X raised to the first power. And while not all natural systems obey this, for small displacements, many natural systems do. And so understanding the simple harmonic oscillator is going to be a very powerful way of understanding what's going on with vibrating systems. Since we have sines and cosines that are going to be showing up in our simple harmonic oscillator, then we're going to be talking in terms of some of the language of waves. So we'll be talking about equilibrium position and amplitude and displacement. And we'll be talking about the velocity of the object and the maximum acceleration that the object experiences. All of these are going to be things that are going to be characteristic of this oscillator. So let's write down some facts about energy in the simple harmonic oscillator. SHO in this context means simple harmonic oscillator. Where is the elastic potential energy of the simple harmonic oscillator the greatest? Well, that's going to be where the spring is compressed the most or is stretched the most. And that's going to be at the amplitude. At the amplitude, the simple harmonic oscillator comes to a stop for just a brief instant in time before it turns around and moves in the opposite direction. So at that point, there is no kinetic energy at the amplitude. Likewise, for a simple harmonic oscillator that's oscillating horizontally, we can say that there is no elastic potential energy at the equilibrium position, because all of the spring is neither compressed nor stretched. So the elastic potential energy at the equilibrium position is 0. On the other hand, when the object passes through the equilibrium position, it's going to be moving the fastest because the object experiences no unbalanced forces at that point. And so what's happening is the object has been accelerated and the object picks up its most speed as it passes through the equilibrium position. And if the object is moving the fastest at the equilibrium position, then that means that the kinetic energy is going to be a maximum at the equilibrium position. Now what about forces? According to Hooke's law, the force is greatest where the spring is either stretched the most or compressed the most, and that happens at the amplitude. And if the spring force is greatest at the amplitude, if that's the only force that's acting, say on this horizontal oscillator, then that means that that's where the acceleration is going to be a maximum. The acceleration is a maximum at the amplitude. On the other hand, there is no force due to the spring at the equilibrium position, and likewise there's no acceleration at the equilibrium position because the object experiences no unbalanced forces. That's what Newton's second law says. Let's see if we can summarize these things in a table of sorts. It looks like there are two extreme points in the simple harmonic oscillator. One is at the amplitude, in other words, the greatest displacement away from the equilibrium position, and the other is at the equilibrium position. Certain things are maximum at the amplitude and 0 at the equilibrium position, and other things are 0 at the amplitude and maximum at the equilibrium position. So here's a table that I've made talking about the force, the acceleration, the speed, the kinetic energy, and the elastic potential energy. And this is for a horizontal spring. So I'm going to complete this table according to these things that we've just summarized here. We're going to use these facts about the spring's force, acceleration, speed, kinetic energy, and elastic potential energy to help us solve some numerical problems. There's one other point that I shall mention right now, and that is that we're going to be dealing with ideal spring systems. In other words, ones in which there are only conservative forces acting. There's no friction. There's no air resistance. We're not going to worry about those things in our problems.